Hi everyone, we're getting into the unit on kinetics. So let's take a look here at a few things that are going to be coming up. First of all, entropy. That's our first thing. It's a measure of disorder. Disorder is how random things are. Everything in nature tends towards entropy, an increase in entropy. And we've got a couple ways that this can happen. Phase changes. So solids are together, liquids are together but closer, they're moving around though, so there's more entropy, they're more random, and then gases are really far apart, they have the highest entropy. Another one is we're going to count. If we have one reactant and we have two products, for you guys it would be the other way around, I believe. One reactant, two products, we've got more products, so therefore our entropy increased. Also, similar to that solid liquid gas, an increase in temperature will be an increase in randomness or increase in entropy. And then we're also looking at simpler, which plays into how many products and reactants. If we have simpler things, that is elements, smaller molecules, that is going to end up changing our entropy. Second big topic we're going to get into is heats of reaction. Now it's called enthalpy, different. This one's got a TH in it. Don't confuse them, please. It's delta H. It's the difference in the products minus the reactants. And here's your equation right here, products minus reactants. And there's a few things you need to know. Heat content, if it's positive, if that change is positive, it's going to be endothermic. If it's negative, it's exothermic. Endo going in, exo going out, like exit. You don't need to memorize it. Thank goodness. You can look at table I, and on the next slide I have table I. So here's part of table I. Gives a reaction, and then it gives you your delta H. This one says it's negative 890.4. Well, I'm going to look at that little asterisk at the bottom. Based on the molar quantities represented in the equation, and a minus sign indicates exothermic, which means that energy is leaving the equation. That molar quantity means if we start with 1 methane and 2 oxygen, this is what we're going to get. If we change those molar quantities, we're going to change our energy. So, endothermic, we're going to absorb energy. Exothermic releases energy. Lots of students exit, exo. And we're going to measure this in heat. We can't actually do this in lab, unfortunately, but you're going to take a look at some of the things. Now, like I said, if we change those molar quantities, we're going to change the amount. So if we have 2 carbon dioxides and we have 556 kilojoules, what happens if we double the amount of carbon dioxide? That means we have to double the amount of energy. And this is just one way to write this equation. Okay. Our final one is potential energy diagrams. Please don't get too confused with these. This is what a potential energy diagram looks like, one version. We start over here. This is number 1. All reactions start with reactants, no different. So here are the reactants. This is the potential energy of the reactants. And then we get it going, and this is our activation. In order to get it going, our activation energy is going up this hill. We can't do anything until we get to the top. So this is the potential energy of the activated complex. Remember, potential energy is going up and down here. That's why I'm reading this as potential energy of the activated complex. And then once we get to the top of the hill, just like if you're biking or you're walking or you're running or you're skating or whatever, once you get to the top of the hill, it's just going to go down. Here are our products. This is going to happen all on its own. Here's our potential energy of the reactants. Now this little part right here, that's our activation energy. That's how much energy it takes to get this thing going. We have to get to the top of the hill before it can go down. And I do have some videos in our folder for you to look at if this doesn't make sense. Not a bad thing to look at them. Now I do need to say, potential energy diagrams can start low and end high, or start high and end low. That'll tell you whether it's endothermic or exothermic. So this, we're starting low and ending high, so we have to end up with a negative potential energy because we start here, potential or H of a product minus H of the reactant. And then here we're starting high and ending low, so we're taking a low number and subtracting a high number. One is endothermic, one is exothermic. Try and figure out which is which. And that is all for today. Those are our 3 main topics that we're going to be taking a look at.